Hi everybody, hope that you're doing well today and that everybody is okay out there. We're continuing with chapter 7 on radicals and radical expressions, and we've taken care of 7.1, in which we gave sort of an introduction to radicals and radical functions. And now we're moving into 7.2, which is unique to the intermediate algebra program. And in 7.2, we're looking at exponential expressions where the exponent is rational. The title of 7.2 is Rational Expressions. And we'll find out shortly that rational expressions, that rational exponents, are linked to radicals. And we're going to see that as we open this up right now on this board. 7.2, rational exponents. We're going to be looking at the definitions of 3 different types of exponential expressions where the exponent is rational. Numerator over denominator. And here is sort of the lead up to the first defined expression that we're going to look at. So let's take a look at this lead up. We've already spoken about this fact that squaring a number, when we square a number, the result that we get when we then find its square root, we come back to the original number that we started off with. For example, if 5 to the second power is equal to 25, then the inverse statement would say, then the radical of 25, the answer that we got from squaring 5, the radical of 25 gives us 5, which just happens to bring us right back to the original number that we squared. So keep your attention on the fact that when we square a number, the result of squaring that number, when we find its root, brings us right back to that original number that we started off with. So let's take a look at a second situation. If 5 to the 1/2 power, when we square that, we're looking at the power of a power. We bring over this 5, and we take the exponent of 1/2 and we multiply it by the exponent value on the outside. That's the power of a power. And 5 to the 1/2 times 2, or 2 over 1, gives us 5. Because these 2's that are right up there, they cross cancel out, and we are getting 5 as our answer. If we now take that answer and find its square root, the square root of this number must be this original base that we started off with. And it is. Because if that wasn't true, then how could this statement up here be true? If 5 squared equals 25, if we do the inverse of that statement, then the radical of 25 is 5, and 5, this answer, matches this base. Well, it's the same thing on this second example. If 5 to the 1/2 squared gives us 5 to the 1/2 times 2 over 1, which is equal to 5, then the inverse statement would say the radical of 5 should be equal to him, 5 to the 1/2. And it is. let's look at one more statement before we make some truths about this. If 5 to the 1/3 to the third power is equal to 5 to the 1/3 times 3, or times 3 over 1, the 3's will cross cancel out. That answer equals 5. Then the inverse must be true. Then the cubed root of 5. Why did I say the cubed root of 5? Because the original base that we took it to the power of was to the third power. So then the cubed root of 5 should be equal to what we started off right here, 5 to the 1/3. Now I'm going to use this example right here to promote really the first defined statement that we're going to be looking at. When you're looking at an exponential expression where the exponent is a rational number, and in this first case, if the numerator of that rational exponent is 1, here are the meanings of each part of this entire power right here. The base of 5 happens to be known as, or called, the radicand of the radical expression. The base of the exponential expression is equivalent to the radicand of the radical expression. Item number 2, the denominator of the rational exponent is equivalent to the index of the radical expression. Notice there's no number in this valley area here, so it's implied that we're dealing with square root, and the number that is associated with square root is a 2. And that just happens to be the denominator of the rational exponent. So, the base of 5, the radicand. The denominator of 2, the index. And the function of the numerator 1 is the exponent. There is only one radicand of 5, or there is only one radical of 5 that we see here. The radicand, the index, the exponent. Same thing on this one. The base becomes the radicand. The denominator becomes the index, and the numerator is the exponent, the number of times, basically, that cubed root of 5 is appearing. These 3 examples lead to the first defined statement, which is defining a to the 1 over n. And here's what this definition says. If the nth root of a represents a real number, so all we're saying at the beginning of this defined statement, this radical expression right here represents a real number. If the nth root of the radical of a represents a real number, and n is greater than or equal to 2, n, the index, is greater than or equal to 2, and it is an integer, the value of n must be a positive number, it must be greater than or equal to 2, and it must be an integer. It's an integer, then here's the definition. A to the 1 over n is equal to the nth root of a. Let's point out the different pieces of this. like we did up there. The base of the exponential expression becomes the radicand of the equivalent radical expression. The denominator is the index of the radical expression, and the numerator 1 represents the exponent. Now there's just one little qualification for this statement. If n is even, if the index is 2, 4, 6, 8, 10, if n is even, the radicand A must be a non-negative number. And that was already pointed out in 7.1. If the index n is odd, if the index is odd for this defined statement, meaning if the index is 3, 5, 7, 9, 11, etc., the radicand A can represent or be any real number. So all this basic rule is pointing out is, when you're looking at an exponential expression where the exponent is a rational number, the base of that exponential expression becomes the radicand of the radical expression. The denominator of the rational exponent becomes the index of the radical expression, and the numerator 1 represents the exponent of the entire radical expression. Now we're going to take a look at about 6 examples that are dealing with this first defined statement of a to the 1 over n. And here's the first direction that we're going to take a look at. Use radical notation to rewrite each expression. So if we're going to follow the directions and do exactly what they're saying, they want us to use radical notation to rewrite each one of these 4 expressions that we're going to look at. And then the follow-up statement, if we are able to simplify, we're going to simplify. So here we go with number 1. We're looking at an exponential expression. It says use radical notation to rewrite it. So we're going to use radical notation. I'm going to get the radical symbol ready. Here we go. The base becomes the radicand. The denominator is the index. Now we ordinarily don't see a 2 there, but I'll put it there. And the numerator is 1. And the numerator being 1, that just specifies the fact that we only have one of them. I'm not going to insert that numerator of 1 anywhere. Now we simplify that if we're able to. If we weren't able to, we'd leave it in that way. But we're able to because the radical of 49 is 7, and that would be that given answer. Number 2, be cautious. It's the opposite of 81 to the 1/2. The only way that base could be negative 81 is if that negative 81 were placed inside parentheses, and it's not. It's an opposite sign, or it's theoretically an imaginary negative sign for negative 1. So we're going to take that negative sign and we're going to bring it down first, and we're going to make a house, because it's set apart from the 81 to the 1/2. Now we're going to take that base and we're going to make it become the radicand. The denominator being 2 is our index. Again, the numerator is 1. You theoretically could put that 1 right there if you wanted to. You could also put that 1 in the upper right hand corner of that 81. We bring down that negative sign. And now we're going to get out of this house. because the radical of 81 can be simplified because the index is 2 and its square root, and we're going to get a negative 9, and we have it. Number 3, we can see that the index is odd. That means the radicand can be any real number. And the radicand can be negative on this one, and it is, because the negative 8 is tucked. So we're going to rewrite it using radical notation. The base becomes the radicand. The denominator becomes the index. I'll just go ahead and wrap it around there like that. And we'll put that numerator of 1 on the outside. It's not going to do anything for us. We're not going to have to work with it. So now we're going to find the cubed root of negative 8. Now, those of you that already know that the cubed root of negative 8 is negative 2, and it should be most of you folks that will know that it's a negative 2, then you can just write down a negative 2 right away. But if you needed to do what I shared in 7.1, this is just an option. You can come down, make the radical symbol, put that exponent of 3 in that upper left-hand corner, and we could prime factor this 8 if you wanted to. If we prime factor 8, that's going to be 2 times 4. And the 4 would break down to 2 times 2, so 8 would become 2 cubed. We can write negative 8 as negative 2 cubed. And because this exponent in this radicand is evenly divisible by the index of this radical expression, we could simply bring down the negative 2, and if we divide this 3 by that 3, we're getting a negative 2 to the first, or just simply a negative 2. And then finally on number 4, if we simplify this or rewrite this using radical notation, we'll get the radical set up. The base, the entire base, becomes the radicand, 5xy squared. The denominator of 4 becomes the index. I'm not even going to worry about doing anything with the numerator of 1 because it's not going to change anything. We have written it in radical formation, and we are not able to do anything with this because we don't have any perfect fourth powers, or we're not able to get any perfect fourth powers out of that. So that's taking exponential expressions with rational exponents and rewriting them in radical notation. I kind of want to erase this little portion right here before we go to that lower right-hand corner right there. Down here in the lower right-hand corner, a second direction. Rewrite with rational exponents. So now we're going to go back the other way. Problem number 1 is written in radical form. We want to write these two problems as exponential expressions with rational exponents. So I'll just situate that number 1 right here. I'm not going to recopy that problem. We'll just put the exponential expression right here. The radicand of 5xy, that becomes your base. So we'll tuck it. Put the fraction bar up there. The index becomes the denominator. And since there's only one of those, the numerator would be a 1, and there's the exponential expression. Number 2, the fifth root of a squared b over 2 will make a quantity. The radicand becomes the base of your exponential expression. So a squared b over 2, put the fraction bar, the index of 5 becomes the denominator, and the numerator is a 1 because there's only one of them. Now that's the definition of a to the 1 over n. That's what we mean by that. Now we're going to quickly, I want to erase, and then we'll go to the second expression, which is sort of a offshoot of the one that we have just now finished. And we'll show you what this is talking about. So over this, on this sheet right here, we're now going to define another exponential expression. A to the m over n. Now simply put, before we actually make the defined statement, in this particular case, a we know is the base. Here's the rational exponent. M and n are going to represent positive integers. The m, however, is not necessarily, or it is not going to be 1. It's going to be some other positive integer, as we will see momentarily. N, he's still going to be our index, as we're going to find out. But in this defined statement, we're looking at where the rational exponent is a fraction other than having a numerator of 1. We'll be looking at numerators that are other integers other than 1. So let's look at sort of a proof statement that's going to lead to something. Let's look at an example of an exponential expression that fits the one that we're going to define. 4 to the 2/3. What does that mean so that we can prove a statement that will lead us to a rule? 4 to the 2/3 can be rewritten in one of two ways. We're going to look at it in this way first. 4 to the 2/3 can be rewritten as the power of a power, whereby it would be 4 to the 1/3 to the second power. This statement right here is him. Because if we bring over that 4 and we multiply these two exponents together, 1/3 times 2 over 1, that's going to give us 2/3. Why did I exercise the right to write it in that way? Because we've already defined what 4 to the 1/3 means. We've already defined that. Before we go down to the next step, we're going to take that 4 to the 2/3, and we're going to express it in another way that's still equivalent to this, by still using the power of the power. 4 to the 2/3 can also be written as the quantity of 4 squared to the 1/3. Because if we multiply 2 times 1/3, that's also 2/3. We're going to come back to this statement right here. Let's go down to this next line. If 4 to the 2/3 is equal to the quantity of 4 to the 1/3 squared, then 4 to the 2/3 should mean the following. People, this base of 4 becomes your radicand. The denominator of 3, that's your index. And notice the function of this numerator. This numerator is the exponent. And that exponent of 2 is placed right on the outside right there. 4 to the 2/3. 4 radicand. The denominator, index. The numerator, the exponent. It's also true here. 4 to 2/3 is also equal to this. The 4 is the base, the denominator is the index, and the numerator 2, instead of placing it on the outside like we did here, we could place it in the upper right hand corner of the 4. Both of these expressions are identical to one another. So, let's make our statement. I've already pointed this out. If the nth root of a is equal to a real number, and m over n, the rational exponent, and m over n is a positive rational number in lowest terms, and n is greater than or equal to 2 is an integer, just like in the previous rule. In other words, let's just summarize. If the nth root of a, if this expression represents a real number, and m over n is a positive rational number written in lowest terms, where n must be greater than or equal to 2, and it must be an integer, then a to the m over n must be equal to this radical expression. The a becomes the radicand, the denominator of n becomes the index, and the numerator m becomes the exponent. Whether it is written in this way or that way, it doesn't make any difference whatsoever. So quickly, on this little part right here, I've covered that rule. Now let's take a look at some examples. Here's the first little direction. Use radical notation to rewrite each expression and then simplify if possible. And here we go. Let's take a look at number 1. 1,000 to the 2/3. Notice the numerator is not 1, but we've already defined what that numerator is. So we're going to simplify this using radical notation. So bring down the radical sign. And folks, I think this is the easier way to do it. Tuck it. The base of the exponential expression becomes the radicand. The denominator of the rational exponent becomes the index. And the numerator of the rational exponent becomes the exponent, which we're going to situate outside. Because notice this for a second before I do it. That exponent of 2 can go there, or it can also go there. Look at the amount of work that you would have to do for this problem to get that answer if you were to do that. You'd have to take 1,000 and square it, and then that result you'd have to find the cube root. It is much easier to leave the exponent on the outside. Now, we're going to simplify this if it's possible, and it is. Because 1,000 is a power of 10. And because there are 3 zeros in this power, in this power of 10, this can be written as such if we need to. The cube root of 10 cubed, and then that answer to the second. Well, notice that this exponent is evenly divisible by the exponent, is evenly divisible by the index, so the cubed root of 10 cubed has to be 10. We bring down that 10, and then we square that 10, and we're at 100 for that given answer. When you write it in this formation, if you can go from here directly down to him and then 100, you do it. You don't need to use that power in there. I just chose to do it, just for the benefit of maybe some people. Number 2, 16 to the 3 over 2. We're going to rewrite this in radical notation first. Make the radical. Put a house. The base becomes the radicand. The denominator becomes the index. And the numerator becomes the exponent. Bring down the house. Put the exponent in place. The square root of 16. We don't need to do anything with 16 to make this thing easier. That's 4. And then we take this base of 4 and take it to the third power. That's 4 times 4 times 4. That's 16 times 4. Done. Answer of 64. Okay, let me quickly do number 3. Number 3. The opposite of 32 to the 3/5. Remember that base is not negative 32, it's 32. That's the implied sign of an imaginary factor of -1, or it's simply an opposite symbol. We're going to bring down that opposite sign, and we're going to make a house. And we're going to form a radical. The base of 32 becomes the radicand. The denominator of 5 is the index. The numerator of 3 is the exponent. Carefully bring him down. Make a house. Keep that exponent on the outside right there. The 5th root of 32. People, those of you that know that the 5th root of 32 is 2, you stick that 2 right in there. But if you have to prime factor 32, if we prime factored 32, if I can just share that, 8 times 4 gives 32. If we were to prime factor 8, that'd be 2, 2, 2. And 4 would be 2, 2. 32 is 2 to the 5th. So if you wanted to do this, bring him down. The 5th root of 2 to the 5th, 5 divided by 5 is 1. It's 2. It's going to be taken to the 3rd, but he's not involved with that. That 2 to the 3rd has to be taken care of first. So we bring down that opposite sign, and 2 to the 3rd is 8, and the overall final answer would be a -8 for that given problem right there. Now just 2 more examples, and then we'll kind of put a close on this portion of the video right here, or this portion of the material in this 7.2, because I don't want to have to come back to this. Let's say that we were going to rewrite with rational exponents. This is the new direction. And let's say we're given this. The radical, the cubed root of 6 to the 4th. The radicand of 6, that becomes the base of the exponential expression. The index of 3 is going to become the denominator of the rational exponent. Take that 6 and bring it down. Make the fraction bar. Index of 3 is the denominator. Exponent of 4 is the numerator. Done. Number 2. Say that we have this. The 5th root of 2xy, and it is being taken to the 3rd. Just writing it in that way. The radicand becomes your base. Tuck it. The index becomes the denominator, and the exponent is the numerator, and we have it expressed in that way. We'll close this portion off right now, and we'll move on to the next area of 7.2. There's a little bit of information in this section, but we'll close it for right now. You take care. We'll talk soon. Bye.